Fiber optic training courses brought to you by sAsA CreatoR. Optical fundamentals training. Physics of optical waveguides. Historical development. 1790 Claude Chat. Optical telegraph system. 1870 John Tyndall. Principle of total internal reflection in a stream of water. 1880 Graham Bell. Developed the photophone voice signals could be transmitted by means of light. 1934 Norman French. Patent for an optical telephone system. 1958 Arthur Shallow. Development of lasers Charles Towns. 1966 Charles Cow. Development of a transmission medium George Hockham. 1970 Corning Incorporated USA. Manufacturing of the first step index fiber attenuation loss less than 20 dB per kilometer with 633 nanometers. 1977 Siemens installation of first optical fiber link of former German Federal Postal Administration in Berlin. Advantages of optical communication engineering. Advantages from the mechanical and chemical point of view. Stability against mechanical effects, example vibrations and impacts. Low weight, 1G quartz glass has the same performance as 10 kilograms of copper. Small dimensions, example core diameter between 8-10 m with SM fiber. Heat, less than 1000 degrees Celsius, and cold do not affect the OWG fiber. The application of OWG is possible without any problems in chemically dangerous places. Advantages considering electrical and transmission aspects. OWG are insulators, therefore no earth circuits will emerge. No risk of short circuit. High security level against tap. Extremely high transmission speed. OWG is corrosion resistant and therefore practically wear resistant. Electromagnetic spectrum. Following are an electromagnetic spectrum chart. Fundamental concepts. What do we understand by a wave? By a wave we understand the propagation of a condition or state of excitement in a material without the necessity of transporting either the substance or components of which the material is made. In case of an optical wave, the condition is the electromagnetic field which propagates within a material permeable to light, example the optical medium. Water waves equals sound waves. What is the refraction index? Factor by which the propagation speed in the respective medium is lower than the speed of air. The refractive index N of a material depends on the wavelength. When using quartz glass, the refractive index decreases continuously within the infrared wavelength spectrum. Important for the optical communication engineering, the more the wavelength increases. Below is a formula. Reflection/refraction. Reflection. Reflection of rays at the interface between two different materials. Refraction. Change of direction, or ray experienced by passing from one medium into another. Total internal reflection. Reflection of all light without refraction when a light ray in an optically dense medium is incident to the interface with an optically less dense medium, whereby the angle of incidence must be greater than the critical angle. The greatest possible launch angle is called acceptance angle. It is only dependent on the two refractive indices N1 and N2. The sinus of the acceptance angle is called numerical aperture NA of the optical fiber. Production. A. Preform production. B. Sintering. C. Drying. D. Melting. OWG profiles multi-mode. Core diameter 62.5 micrometer. 50 micrometer. Core refractive index 1.48. Cladding diameter 125 micrometer. Cladding refractive index 1.46. Easy splicing, only outer diameter has to be aligned. Lower distortion of propagation velocity than for step index, multimode. OWG profile single mode. Core diameter 9 micrometer. Core refractive index 1.475. Cladding diameter 125 micrometer. Cladding refractive index 1.471. Splicing only with special equipment. No distortion of propagation velocity. No distortion of pulse. OWG profiles. Single mode fiber. Human hair. Multi-mode fiber. Modes of light. Following are modes of light chart. Attenuation. Attenuation is the loss of light power in an OWG transmission link. The fairer a signal is transmitted, the less light reaches the receiver. The attenuation value is measured in Bell and expressed in tenths of A. Bell or decibel, dB. This unit is applied in terms of amplification and attenuation. Attenuation, dB, equals 10 log 10, power input / power output. Indication of power equals dBm. dBm equals 10 log 10, power / 1 MW. Attenuation causes scattering. Inhomogeneities in the material occur during manufacturing process. Absorption. Loss of radiation during transit through a medium. In case of light, part of the radiation energy is transformed into heat and other forms of energy. Radiation. Micro-UND macro bending of the fiber. Rayleigh attenuation. Rayleigh scattering. Appears within microscopically small scattering centers, 1 m, and depends extremely on the wavelength of the light. When the light reaches the point of perturbation, a part of the guided light is scattered in all directions. Absorption. When light hits 0 N impurities in the core and is consequently absorbed. Absorption because of the electrons of the material UV absorption. Absorption due to material intrinsic vibrations of the glass IR absorption. Absorption which arises only in certain wavelengths depending on the properties of the material. Resonant absorption. Microbending is a microscopic bending of the fiber which causes that light scatters from the core into the cladding. Microscopic bending caused during manufacturing process. Variation of temperature. Macrobending. Bending of fiber to a larger scale, which falls short of the allowed bending radius, causes that light is coupling out of the core. Visible bending. Light rays exceed the critical angle. Higher impact in case of bigger wavelengths. Bending. Bending attenuation. Attenuation 1310 nanometers. Attenuation 1550 nanometers. Attenuation 1625 nanometers. Bending diagram. Attenuation of the fiber banding. Macrobending. Absorption. Microbending. Optical windows. Following is an optical windows chart. Dispersion. In the optical waveguide technique, dispersion stands for all effects produced by light pulses which broaden in time when they propagate through an optical fiber. Telecommunication transmission with optical waveguides. Transmitter. Preamplifier. Transmitter diode. Fiber optical cable. Splice. Connection. Receiver. Receiver diode. Amplifier. Electrical signal. Optical signal. Coupling attenuation. Splice attenuation. Coupling attenuation. Electrical signal. Thank you for watching. We will back soon with next fiber optics learning videos. Please like and subscribe our channel.